quickly discuss extensions to finite volumes. One is actually to solve systems of equations, system of conservation laws. So here, I'm just really quickly giving you an example of a system of conservation laws, and you can generalize, imagine from there. So a system of conservation laws is something that can be written as this. A time derivative of not just the one thing, but two things, u1, u2, is equal plus the spatial derivative of also two things, f1, which is a function of u1 and u2, f2, which is another function of u1 and u2, is equal to 0. Okay. Of course, you can go more complex and say there's f1 and f2 not only depend on the value of the u's, but also depend on the derivative of the u's. That would be a conservation law that involves the second order spatial derivatives, because f is a function of the spatial derivative of u, and in the differential equation we're differentiating that to space again, right? But to start with, let's just look at this equation. A prominent example, well, one example is the gas dynamics equation, because in gas dynamics, the Euler equation and Navier-Stokes equation, we have actually not only two variables, but more than two variables. We have the conservation of mass, where the conserved variable would be density, right? Because when you integrate density, you get the mass. So the conserved variable for mass conservation would be density. We also have energy conservation, and the conserved variable for energy conservation is the energy density. It's the density where if you integrate the energy density in space, you would get the total energy within a certain control volume, right? So second equation. We also have conservation of momentum. And in conservation of momentum, the conserved variable is momentum density. It's the unit amount of momentum within a unit, it's the amount of momentum within the unit space, unit amount of space. So that's the momentum density. So you have all three equations coupled together, right? Your conservation of mass actually would, the flux of the mass depends on momentum because it depends on the speed. The conservation law of momentum actually depends on energy, right? Because in momentum equation, you have pressure acting, changing the momentum. It's a force, right? And pressure depends on energy, depends on the internal energy. So that way it's coupled. And the conservation of energy also depends on momentum. It also depends on velocity, right? So basically, three equations are all coupled together. It's impossible to disentangle, like untangle all the three equations. But in this case, let me just give you a simpler example from the gas dynamics equation. It's called the shallow water equation. That's another example of a system of conservation laws. So I'm just going to give you a physical derivation. So let's say we have a shallow water forming. So this is x, and this is the height of the water. Okay, and of course, when you have water not forming a uniform height, the water would not sit in stationary form. So the water would move. So at any point, you would move, the water would be moving either towards the left or towards the right. So you have a velocity of the water. And the shallow actually means that the velocity from the top and bottom are actually the same. So basically, you have no variation of velocity as a function of the height. So that applies to shallow water. So you have velocity here. And now we can look at the conservation, right? We can look at conservation of mass and conservation of momentum. Okay, so conservation of mass basically says that, okay, so if I, the shallow water equation also assumes the water is incompressible. Okay, so when you have left and right, and if I integrate the total amount of height, right, that actually is the entire basically area of the cross section of the water. So now if you take the time derivative of the total area, what is it equal to? Well, it's equal to how much water is getting in from the left interface minus how much water is getting out from the right interface, right? So if you write it down, it'll be H times U, right? L and R. So it's equal to basically the height of the water times the velocity on the left. That's the flux. That's basically the flux of amount of water. So that's the first equation. All right. And then we also have conservation of momentum. So how do we express the total momentum of water within this between L and R? Well, we can write it as the density of water, right? Okay, times the height times U. So this is the momentum of water per unit depth, right? So times dx. So here I'm integrating over two spatial dimensions, and I need another spatial dimension to actually get the momentum. So this is actually not the momentum, but the momentum per unit depth in the direction perpendicular to the whiteboard, to your screen. Okay, so the momentum is equal to the momentum flux, right? Which is the momentum flux over here minus momentum flux over here. And the momentum flux is, of course, a velocity times the momentum, u times rho h u. So that's the raw flux of momentum, and also plus force, right? The force is basically the pressure force, the average pressure force on the left-hand side. And the average pressure force on the left-hand side is actually the gravity times the half of the height, right? That's basically, and half of the height is basically g times h times rho. So that's basically the average pressure, right? And the pressure acts over a height of h. So that's the pressure force. The pressure force and momentum flux carried by the water coming in. So this is also take the difference between L and R. That would be the flux function of momentum. So here I basically have derived the differential equation in its integral form. And if you want to write it in a differential form, you would be saying that, okay, so I can denote this as a flux with a subscript h. I can denote this as a flux with a subscript of, let's see, momentum, okay? And this is h, and I can say this is momentum. Then the time derivative of h and m would be equal to, well, let me just have this on the left-hand side, d dx of fh and fm equal to 0. So here fh would be equal to what? Would be equal to m divided by rho, right? And my fm would be equal to, well, what I have to do is I have to write this complicated formula as a function of h and n, right? And here I have 2u, so the first term has to be n squared. The m squared would be have a rho squared, the h squared, the u squared. So to compensate, I have to divide by rho and divide by h. Okay, the second term is basically half of rho g h squared. So this would be completing our task of writing the flux as a function of the conserved variables.